Hey math people, Fundamental Theorem of Calculus. Obviously with the title like that it's got to be pretty powerful, so let's talk about the two parts to it. I want to kind of show some big ideas with the first part using the second. This is mostly focused on this guy right here. So if I want to take the derivative, d dx, of the integral from a to x of f of t dt, I can do this. And it's actually equal to good old pretty just f of x. This is part one of the Fundamental Theorem of Calculus, depending on what textbook you use. Part two says, well, if you're integrating from a to b on some sort of curve f of x dx, then you can evaluate on the bounds, you can evaluate the antiderivative on the bounds. So typically we say the antiderivative of little f is capital F, so we might say, well, big F of b, plugging in that first, that upper bound, we would then subtract off the lower bound, big F of A. This one is the one that most people are pretty good at. It's the one that you use more often than not. Although today's focus is going to be on this one. So let's show this. I want to show this. So I'm going to drag this guy on down for a sec. Let's show this. So I'm going to take the derivative of the integral from a to x of f of t dt. All right, this in itself ain't too bad. Let's plug in these bounds using FTC part 2. And I'm going to do it over here. So actually, let's do this. So d dx stays. You don't go anywhere. And if we plug in the upper bound, we'd have f of x. And we'll write it as capital F of x as the antiderivative. And then we're going to subtract off capital F of a. It's the antiderivative evaluated at a. Which is going to be a number, and that's really important right now. This is a function. It's essentially just the antiderivative, and this is the antiderivative evaluated at a, which is just a number. So if a was, like, say, the number 3, the antiderivative evaluated at 3, who knows, it might be just literally the number 7. So at the end of the day, this is a constant. It's a normal run-of-the-mill number. And when I take the derivative of minus 3, what is the derivative of just good old 3? It's 0. It actually ends up going away. So the derivative of the antiderivative, well, you're back to yourself, which is the result I stated earlier. But now, what if we run into this problem? What if we have the derivative from a to some sort of function? So maybe you're evaluating from 3 to x squared, or you're evaluating from negative 7 to sine of x. What does that mean? How does that change our problem? Well, you're about to see. And I still want to do the same thing. So, f of t dt. Okay, same story. Let's just evaluate on the bounds. So the derivative, now we're evaluating on the bounds here, so we'll say f, or big F, right? Because we're looking at the antiderivative now. Big F of the upper bound's g of x minus big F of the lower bound, which is a. And this is nice because same story occurs for a. This just kind of goes out, kind of cancels away. So finishing up this problem here, taking the derivative of the antiderivative of f, so that would just be lowercase f, same story here. Except now I have this function inside of a function. So if I'm taking the derivative of a function inside of a function, what does that call for if we remember our derivative rules? It calls for the chain rule. So sure, I took the derivative of the outer, now I need to multiply it by the derivative of the inner. So what are the 3 scenarios we can run into when dealing with FTC problems? If we have an upper bound of just x, we like that. That's the easiest case. All we have to do is really essentially just plug in x for t, and then that's it. Note here the lowercase f is f's. All right, what about if we have an a? So if we're evaluating on a lower bound, I'll just I'll box it over here. You'll note if we're evaluating on a lower bound of a constant, and it actually could be an upper bound too, by the way, if it's essentially just a constant, you'll note that it always goes away. It always cancels out. So here it canceled, I'm just kind of assuming it canceled over here because it did. Anytime you have a constant, well, the constant will just be ignored because you're taking the derivative of a constant. So this guy always, he takes out all constants, right? He always makes them 0. Any ddx of a constant will always make it 0. And then, so that's the constant case. This is the x case. And then the final case, what if you have a function in a bound? Well, then you have to do this. And this is the worst case. Here, when you're evaluating and when your bounds is a function, this is what you need. When you're evaluating and when your bounds is just x, you don't have to do anything. You're pretty much just putting it in for t. And when you're also evaluating on a constant, well, it just goes away. Those are the 3 cases we need to know for FTC. Okay, so looking at our first 2, easiest 2, by the way. Number 1 is like a 10-second problem. We're looking for the derivative of this expression, which happens to be an integral. So the first time we encounter problems like this, we can just start by taking the derivative of both sides. The derivative of f. So what am I doing right now? I'm taking this whole thing, and I'm taking the derivative, ddx, of both sides. So, on the left, derivative of capital F, well, it's just f prime, capital F prime, and I can write this as lowercase f. It's conventional to do that. Derivative of capital F is lowercase f, but just keep in mind it's just a convention, so some people might not interpret it that way. Alright, and I want to take the derivative of this right side, so I'm just going to put ddx, the integral from 1 to x, of t cubed minus 4t squared plus 5 dt. Okay, so moving onward, I see a constant down below, and we don't care about constants in situations like this. If I take the derivative, this is eventually going to be the antiderivative of this expression evaluated at 1. That's just a number, so I don't care about this. It's going to be 0. I do care about the x, though. I do need to plug this into this expression. So since I'm taking the derivative of the integral, I can just straight up plug in the x for the t's, and that's the whole problem. And really, it's no work at all. That's the answer. Derivative of the integral of this expression is itself. So f prime here, x cubed minus 4x squared plus 5. You'll see that we're not quite as lucky in number 2, though, because the upper bound is a function. It's x cubed. It's not just x, so we do need to apply the chain rule because of the result we saw like 2 minutes ago. Constant I don't care about, so it's going to end up going away. I'm going to say capital F prime of x is equal to ddx of the integral from 2 to x cubed of t squared minus 8t plus 15 dt. I'm just simply rewriting it. I know there's a glare over here, so all I did was rewrite it. With ddx in front. Alright, so I have this upper bound of x cubed. All I need to do is plug in this x cubed just like how I plugged in the x over there. The only small caveat is the chain rule. I need to then multiply by g prime at the end, in which case my g of x here is equal to x cubed. So with that said, that'll be a little helpful. So what am I going to multiply off to the side? What is my g prime here? It's the derivative of x cubed, which is 3x squared. So what's going to happen is I'm essentially just going to plug in this x cubed, and then tacked off to the side will be this 3x squared. And I do have to distribute it in, which, you know, it's a process, but nothing too crazy. So this is equal to, so I'm plugging in this x cubed. It'll be x cubed squared minus 8 times x cubed plus 15. And then I have to multiply by g prime. I need to multiply by this guy by chain rule. 3x squared is on the outside there. I do have to distribute this in. So this is x to the 6th. So this would be 3x to the 8th. This is going to come out to negative 24x to the 5th. And this is going to come out to 45x squared. Being the final answer for capital F prime here. So I really want to convince you of this a little bit further. This idea is very strange to a lot of people. The fact that we have to take the derivative of the functioned bound and multiply it in, it's weird for a lot of people. Okay, but people are typically good at FTC part 2. So what I want to do is I want to view this through a different lens. What if I want to deal with it this way? I'm going to say capital F. So this is just another approach to it, and we're going to get the same result. Capital F prime of this expression, I'm just going to deviate from this path. So let's just say I don't like this dashed line. Let's just say I don't like this. It's a little abstract. That's fine. We'll show you the part 2 way. So that's with FTC part 1 down here. I'll show you the part 2 approach. It's a little bit longer though, so you can skip this if you want. If you want to just jump to 3, you can. But I think the connection's pretty cool. So I'm going to just plop down this ddx, and I'm going to actually find the derivative, or the antiderivative of this expression, and evaluate it on the bounds. So let's just worry about the antiderivative for now. Antiderivative of this is going to be 1/3 t cubed minus 4 t squared plus 15t, and then of course I'm evaluating this from 2 to x cubed. Okay. So I want to put in my bounds now. I want to put in my upper bound and my lower bound. So I'm going to do that. The ddx is still just sitting up front. I'm waiting to apply that till I simplify the integral first. So I'm going to end up getting 1/3. So this will be x cubed, so it's going to be x to the 9th there. Minus 4 times x cubed squared plus 15 x cubed. And oh no, I've run out of space and I have a whole lower bound I need to worry about, right? I need to subtract off what would happen if I plug in 2, but not really. Because if I plug in 2 to this expression, sure, you end up getting like 8 cubed minus, what is that? Minus 8 plus 30, whatever that number is, and sure, we would be subtracting it off, because that's how FTC part 2 works. However, it's just a number, and I'm going to take a derivative of it anyway, so I'm just going to say plus, and you could put plus c, but I don't want you to get confused with what that might be. I'm just going to say plus some sort of number, whatever the result of that actually is. So it's probably going to be a negative, because you're doing the antiderivative evaluated at b minus the antiderivative evaluated at a, but it doesn't matter at the end of the day because we're going to get a constant. So when I take the derivative of this expression, which I'll not do in this step, by the way, because I want to pretty up this process by the algebra, I get 1/3 x to the 9th minus 4 x to the 6th plus 15 x cubed plus number. Now let's take the derivative. Derivative of this expression is 3x to the 8th. Derivative of this expression is minus 24x to the 5th. And then finally, we end up getting 45x squared here. And hey, would you look at that? It's the same exact, hopefully, right? Same exact expression. So you can feel free to do these problems this way if you'd like, if you're more of a FTC part 2 kind of person, but I just think this way is so much faster, and you don't have to do all this tedious algebra here. So I'm going to kind of advertise this approach right here. Get comfortable with FTC part 1, and you can just fly through some of these problems really quickly. Okay, looking at 2 more, and both of these are beginning to get pretty tricky, because now we don't have any constant in the bounds, which means we do have to use the part 2 aspect of this to the fullest extent here, because we do have to take the antiderivative and evaluate at the bounds and then take the difference between the two. So to clarify what I'm talking about here, this guy. So I am going to plug in these bounds, and you will see a difference between them. Just keep in mind, though, that these two are functions of x, and I'm going to have the chain rule used in both of them. So this is where it gets fun. But again, if you kind of know the process conceptually pretty well, it's really nothing too crazy. Because here I'm saying, okay, well, f prime of x is equal to ddx of this expression from x to 2x, 4 over t dt, derivative of an integral, FTC part 1. I'm plugging in this 2x here for this t. However, chain rule derivative of g of x, which is our upper bound here, it is a function. The derivative of 2x is just 2. And then I'm going to subtract off. What am I subtracting off here? What would happen if I plug in x? So it'll be 4 over x. We like the x cases, not a lot of work to do there. So I do see this minus from FTC part 2 over here. And let's clean this up. These 2's cancel. Those go away. I get 4 over t minus 4 over t, and actually the derivative of this is just 0. Okay, so 0 was a really suspicious answer. I picked this problem intentionally because I think it's kind of cool. I'm thinking Scooby-Doo here. I want to just take the mask off of this expression because I want to see what this really was. Who's really hiding behind this? So I want to actually just integrate this. I want to use just part 2 of FTC. This guy right here. And I want to see who you really were. So the derivative is not helpful here. The antiderivative of 4 over t is 4 natural log t. So 4 times natural log of, it's actually technically the absolute value of t, but I don't think it'll be relevant for this problem, by the way, after we see what happens. Alright, let's plug in our bounds. So this will be 4 natural log of 2x minus 4 natural log of x. Alright, so let's do some log properties. We end up getting, we can just factor out the 4. Yeah, if we just factor out this 4, we'll have natural log of 2x minus natural log of x. And if you're taking the difference between two log expressions, you can take the quotient of what those two expressions are. So I'm going to write this as 4 times natural log of 2x over x. And technically, sure, it's in absolute values, but it's not going to matter because right now, these x's go away. I have 4 times the natural log of 2, and let's just be super extra about this. This is going to be natural log of 2 to the 4th, which is natural log of 16. And I was taking the derivative of natural log of 16. So what is the derivative of just a constant, a number? Voila, it's 0. Alright, let's finish up this last guy and call it a video on FTC. So, same story. We'll do f, capital F prime of x is equal to d dx from x to x squared of 3 over t minus 1 all squared dt. So, upper bound, I will need to use chain rule here. So I'm going to plug it in though first. It'll be 3 over x squared minus 1 all squared. And then now chain rule, so the derivative of x squared is 2x. And then minus, what would happen if you plug in x? Because again, remember, FTC part 1, I'm taking the derivative of an integral here, so it's going to be 3 over x minus 1 squared. Okay, so let's pretty this up. It'll take just one step, because my numerator here is now going to be 6x over x squared minus 1 all squared minus 3 over x minus 1 all squared, being our final answer. Yeah, so FTC, once you get fluid with both part 1 motions and part 2 motions, it becomes second nature. But until then, I really think you should try to conceptually grasp it first. So the proofs that I did were not only short, but really not that rigorous. I think it's worth your time really investing in figuring out why the relation between the two really exists. And all of a sudden these problems will be a lot easier after that. So that's all there is for this video. I'm going to ask you to continue the math on, and I will do the same. I'll see you in the next video.